Howdy! Chapter 5, Applications of Gauss's Law. As you will see in this chapter, you will sometimes be able to find the electric field easily using Gauss's law, where it would be virtually impossible to do it any other way. The difficulty in using Gauss's law is in finding the right surface to integrate over when evaluating the left side of this powerful law. One common mistake is trying to use the law without drawing the Gaussian surface you are integrating over. This normally spells failure. Finding the right surface starts with knowing the positions of the charges that produce the electric field. We will limit ourselves to two extreme cases. Perfect insulators, where charges are fixed and cannot be moved. Perfect conductors, where charges are totally free to move. For insulators, we may be given the charge distribution, while for conductors, we will have to figure out where the charges reside. In either case, we start with determining the symmetry of the electric field from the distribution of charges, and that tells us how to choose the surface so that we can find the value of E at any point. This is going to seem very complicated and panic could set in. The good news is that there are only 3 charge distributions where a useful surface can be found, and the symmetry for these 3 will be discovered in the chapter. You will not have to invent the appropriate surface yourself for any other distribution. This is also the bad news, since it is going to be very nasty to try to find the E field when you can't use Gauss's law. The 3 distributions that will be studied are spheres, cylinders, and planes. The electric fields for these 3 distributions will be found to be spherical, cylindrical, and planar. Once these are explained and you have done some problems for each of these 3 cases, they will seem pretty obvious. The appropriate surfaces will enable you to get the magnitude of E out of the integral. That is the whole idea of using Gauss's law. Having drawn the appropriate Gaussian surface, there are 2 possibilities for the right side of Gauss's law. If you are dealing with a perfect insulator, the charge inside should be straightforward. If you are dealing with a conductor, you need to figure out where the charges are located in order for them to be at rest. This means there is no force on the charges inside of a conductor, so the electric field must be 0. You will see that you can use Gauss's law backwards, knowing the electric field is 0 to figure out where the charges are. Given the resulting E fields, we will be able to calculate electric potential differences for realistic charge distributions and begin the study of circuits with real devices. Summary. The rather incredible law derived in the last chapter is the integral of E dot ds over a closed surface is equal to the charge inside over epsilon 0. The first step in applying this law to find E is to draw the appropriate Gaussian surface to integrate over. This can only be done for symmetric charge distributions, either spherical, cylindrical, or planar. The magical surface will enable you to get the magnitude of E out of the integral. Once having drawn the surface, finding the charge inside should be simple. Gig 'em!